Okay, let's get started. So today we're gonna be talking about related rates, which is a type of word problem that you now have the tools to solve. And these can come up in a lot of different contexts. But there's sort of like the method for solving them is always pretty similar. So I'll start off with just like an explanation of how these go, and we'll do a couple of examples at the board. And then in like the second half of class, I'll break you up into groups to work on problems together. So at the boards, there's a related rate problem for each group. So yeah, about halfway through lecture, I'll split you up into groups and you'll work on the problems together. Okay, so what is this all about? So let's take an example. So let's say we're pumping air into a balloon. Okay, so we have a balloon and we're pumping air into it. Okay, so there's sort of two relevant quantities. There's like the volume of air that the balloon contains, and then there's also the radius of the balloon. And the rates of increase of these two things are related to one another, right? So the volume and the radius, their rate of change is related to one another, right? Because if I'm pumping air into the balloon really quickly, then the radius is also expanding a lot more quickly. Whereas if I'm pumping air into the balloon slowly, then the radius will only grow slowly. So both are so as we pump air into the balloon, both of these quantities are increasing, and they are related to one another in some way. And sort of the motivation for these types of problems is that typically in a real life application, one of the quantities will be easier to measure than the other. So for example, if we're pumping air into a balloon, we might be using a device that pumps a fixed volume of air per second. And so then we can, from that information, we will be able to actually calculate the rate of change of the radius of the balloon. So what we will do is find the rate of change of the radius using the rate of change of volume. Okay, so let's actually I'll just state a problem related to this and then we'll go through how to solve it. So let's say air, so here's the problem. Air is being pumped into, we're going to assume that the balloon is spherical because typically with these problems, you need to know some kind of equation that relates, like in one that relates to volume, you'll need to know an equation for the volume of the object that you're looking at. And so we're going to assume that it's spherical because that is something that we have an equation for the volume of. Okay, so we'll assume it's being pumped into a spherical balloon at a rate of 100 centimeters cubed per second. Okay, and then we're going to ask how fast the radius is changing. at the time when the radius is 25 centimeters. Okay, so this is our question. And so the idea for how to solve these is that so the quantities that we're interested in are the volume of the balloon and the radius of the balloon. So we will relate those two quantities using an equation. So in this case, it'll just be the equation for the volume of the balloon. And then we'll take the derivative of both sides of that equation with respect to time. And that will give us an equation that relates the rates of change of the volume and the radius. And the key kind of idea here is that the derivatives are the rates of change of these quantities. So I'm going to give you like some steps to work through these problems. So the first step is to define the relevant variables. So we'll define, so step one, define some variables. So in this case, we'll let V denote the volume of the balloon, and we'll let R be the radius. And then I'm just going to kind of reframe the problem in terms of these variables. So we are given, let's let T be time. So the quantity that we are given is the rate that air is being pumped into the balloon, which is dV dt. So we are given dV dt, and what we want is to know the rate of change of the radius. So we want dr dt. Okay, is this making sense so far? Okay, step two, we have to relate the variables. So the volume of the sphere right, so there's a way to know the volume of the sphere in terms of the radius of the sphere, and that is that the volume is equal to 4/3 pi r cubed. By the way, I don't expect you guys to just know these volume formulas off the top of your head. So if one was like needed on an exam or something, I would just provide it for you. Like some of these problems involve like the volume of a cone or something. So yeah, if you need to know a volume formula, I would say just like look it up on Google or something like that doing these problems, and otherwise I would just give it to you. So that's the volume of a sphere. And then we're going to differentiate both sides. With respect to T. So basically when you're doing this, you should view V and R both as some kind of mystery function in terms of T. And so then when you take ddt of both sides, you'll chain rule the V and the R. So look, we'll do dV ddt of V. This is going to equal ddt of 4/3 pi r cubed. Okay, so then when I take the derivative here, I'll get, this will just be dV dt, and this is equal to 4/3 pi. So for the r, we'll have to power rule and then chain rule. So we get 3 r squared dr dt. Okay, maybe I'll pause here. Are there questions about this stuff? Yeah.
I guess I was a little trying to figure out like channel rather than just being power. Is that because you're differentiating respect to T, so you kind of
Yeah, like R, if you think about it, R is some function of T, right? Like as time goes on, the radius of the balloon is changing. So yeah, that's why we have to use the chain rule, is because this is something that, this is like a quantity that depends on T. We're taking the derivative with respect to T. Does that answer your question? Okay, are there other questions? Okay, so then, right, so going back to the problem statement, we wanted to know the R dt given the VDT and a specific value of R. So now I'll just rearrange the equation to solve for dr dt. So step 4, we'll just isolate. So we're going to solve for dr dt. Okay, let me just simplify this a little bit. So these two 3's cancel each other. So then we get that dr dt is equal to 1 over 4 pi r squared times dv dt. Okay, so then the last thing we need to do is plug in. Oh, yeah, you were.
Why is it? Isn't it just 4 pi r squared?
I'm moving it to the other side of the equation, and then I also change the order. Yeah.
Oh, I see.
Yeah. Are there other questions? Okay, so then we just have to plug in. Nope. So we were given dv dt was 100 and r was 25. So we get dr dt is equal to 1 over 4 pi times 25 squared times 100. Okay, and if you simplify this, you just get 1 over 25 pi. And then you have to think for a second about what the units are. So the radius would be changing. Everything was in terms of centimeters. This is centimeters per, I think it was, everything was centimeters per second, right? Yeah. Okay, so this would be the final answer. Okay, are there questions? Yeah. No, so the exam will cover content up through the end of lecture on Friday. Those, it'll be on the next midterm and the final and stuff, but yeah. Yeah, question? Yes, okay, so let's think through this. So I'm just gonna go back into this equation and plug in the units as well. So this was centimeters cubed per second, and this was centimeters. So down here we have centimeters squared in the denominator, and here we have centimeters cubed per second in the numerator. So the centimeters squared will cancel, yeah. Are there other questions? I think one nice thing about these problems is that you can do a little check, like at the end. It makes sense that this was like a positive number, right? If we got a negative number, then I'd be thinking, okay, I probably went wrong somewhere because I know the radius of the balloon isn't decreasing. as I pump in air and things like that. So that is just a little check you can do to make sure, like, you just think about, does my answer make sense in the context of the problem? Okay, do y'all want to see me work another example at the board, or do you feel ready to try to do the problems yourselves? Sorry, another example? Okay, I'll do another example, and then after that, I'll break you up into groups to work on problems. Are there other questions about this example? Okay, so we'll do another one. This one's kind of different. It doesn't have to do with a volume. So for this one, we're gonna have a 10-foot ladder, and it rests on a vertical wall. And the bottom starts sliding away from the wall. At a rate of 4 feet per second. And the question is, how fast is the top sliding when the bottom is at a certain distance? So how fast is the top sliding when the bottom is 6 feet from the wall? Okay, so when you get a question like this, a lot of times it's helpful to just draw a diagram of what's going on. So here's like the wall and the floor, and then we have a 10-foot ladder resting. And we know that the bottom is sliding at a rate of 4 feet per second. And we want to know what is this rate whenever the bottom is 6 feet from the wall. Okay, does the question make sense? Okay, so the first step that we need to do is to define what variables we're going to use. So the relevant quantities here are like the distance of the bottom of the ladder to the wall and the height of the top of the ladder. So I'm just going to call those X and Y. So we'll let X be the distance of the bottom of the ladder to the wall. And I'll let Y be the height of the top of the ladder. So in my picture, this quantity is X and this quantity is Y. Okay, and then we're given the X dt, and we want to know dy dt. Okay, does this setup make sense? Okay, so for our next step, we have to relate the quantities x and y. So how could we do that? I think this is the hardest step sometimes. Yeah,
Use like the Pythagorean theorem.
yeah, exactly. So the Pythagorean theorem will give us a way to relate x, y, and the hypotenuse of the triangle. So we get x squared plus y squared is equal to 10 squared, which is 100. Okay, are there questions about that? Okay, so now let's differentiate both sides. We'll take d dt of x squared plus y squared is equal to d dt of 100. Okay, so what do I get for this left? The left-hand side of this equation, what is d dt of x squared plus y squared? Yeah. 2x times dx dt plus 2y. Yeah, so 2x dx dt plus 2y dy dt. Okay, good. So that was just power rule followed by chain rule for each of these. And then what about for the right side of the equation? Yeah, that's just gonna be 0 because we're taking the derivative of a constant. Okay, so then we need to, okay, yeah, right. So we want dy dt. So I'll just isolate dy dt in this equation. So we get dy dt is equal to minus 2x dx dt. So just moving that to the other side of the equation and then dividing by y, 2y. Okay, and then last thing I want to do is plug in. So we have what did the question ask us? So it wanted to know how fast is the top sliding when the bottom is 6 feet from the wall. So we'll have x is equal to 6 feet and dx dt was 4 feet per second. Oh, and we're also going to need y, right? Because so I have dy dt written in terms of x, y, and dx dt. So how do I get y? Going back to the diagram. Let me actually just copy this. Yeah. Yeah, exactly. So we'll just use the Pythagorean here again on this triangle with x is 6. So maybe I'll do this in 2 steps. So we know that y squared plus 6 squared is equal to 100 squared, or sorry, 10 squared, which is 100. So y squared is equal to 100 minus 36, which is 64. So y is equal to 8. Well, I guess it's, okay, so it's plus or minus 8, but we know it's plus 8 because it's like the height. Okay, so now we have all these things so we can plug into our equation, and this will be 8 feet. So we got dy dt is equal to, the 2's will cancel each other. So we get minus 6 feet divided by 8 feet times 4 feet per second. So, what does this simplify to? Minus 3 feet per second. Does it make sense that we got a negative number? Yeah, because, this height is decreasing, right? So that tells me that I should get a negative number. If I got a positive number, that would mean that somehow the ladder was moving up the wall, which sort of isn't the situation that we're in. Okay, are there questions about this example? Yeah.
Could you one more time where the negative sign came from?
The negative sign came from when I rearranged this equation. So I took this to the right-hand side and that's where the negative came from. Yeah. Other questions? Okay, sounds good. So here's what we'll do. So I have the boards divided up into 7 sections and they each have a chalk and a problem.